Hello, everyone. Let's start today's session. I hope you started a great day. Uh, Following the previous session that we had, there was an example that we couldn't finish, and I find out what was the problem. It was like a very simple, like a typo that I did, and I couldn't figure out what happened. Now, I am gonna start over. So we are actually clear on that example and how we uh, can develop the state space from the transfer function. And then we are going to move on to the next concept, which is converting the state space to the transfer function, like the other way around. Okay, so let's start with this example and try to solve it again. Now, as I mentioned, uh, in this example, okay, my aim is to not just develop the x dot, the equation x dot equal to ax plus bu, but also I want to have the output. So I want to also have the equation y equal to cx plus du. Now, how to do that is very simple. We already learned how to deal with the block diagram, and we know we can separate the such a transfer function, such a block diagram, into two series block diagram. So I can have two series block diagram starting from the input and ending from to the output. The first one, I am going to use the denominator. Okay, so I am going to say it's 1 over s cubed plus non-s squared plus 26s plus 24. And the second one would be the denominator. So it's going to be s squared plus 7s plus 2. Now, here, between the two, I am going to define another vector, which is the output of the first block diagram, and I'm going to call it b of s. Okay, now, if we wanted to represent the b of s based on the input, so if we want to say b of s based on the input, we can easily see that it's going to be that transfer function inside the block diagram, 6s plus 24. So when we have this, we can basically write it in a simple equation. So we are going to move the rs to the one side of the equation, and it's going to be equal to the bs, b of s times that denominator is cube plus 9s squared plus 26s plus 24. Now, what we have to do is when we talk about that, when we reach such an equation, what we are going to do is to take a inverse Laplace from such an equation. So the inverse Laplace of the input, we are simply going to represent it by the time function of that input. And then we are going to have s cubed times b, which is going to be the third order differential, okay, third order differential of b. Okay. Now remember, we said that b dot, if we want to get the Laplace inverse, okay, is gonna be sorry, the SP is gonna be b dot minus initial condition s squared b is gonna be b double dot minus s b B dot 0 minus B 0, and also SQ is going to be triple dot minus S initial condition of the double dot minus this SQ. S initial condition of B dot minus the initial condition. But since we are talking about transfer function, we already said that all the initial condition we assume to be 0. So all these parts are going to go away. All these parts are going to go away. So that being said, we know that the SQ B is going to be B triple dot. S square B is going to be B double dot. Same goes for the SB is going to be B dot, and then we have 24 B itself. Okay, now again, if you remember about our discussion about the state space, we said that when we have a third order differential equation, okay, since we wanted to have 3 one-order differential equation to develop the state space, that means we need 3 linearly independent state variable. Okay, so we are going to define our state variable as x1, x2, and x3. x1 we are defining as B, x2 as B dot, and x3 and as B double dot. Okay, if we have such a definition, then the x1 dot is going to be B dot, which is x2. x2 dot is going to be B double dot, which is x3. And x3 dot is going to be B triple dot. We don't have that in a state variable, but we have the original equation. So it's going to be minus 9 B double dot, which is the x3, minus 26 B dot, which is the x2, and minus 24 B, which is x1, plus RT. I moved everything but B triple dot to the other side of the equation. Are we good so far? Is that clear what we did? Okay, now we have everything we need for developing that famous x dot equal to ax plus bu. Now, let's actually do that. So our x dot vector is going to be x1 dot, x2 dot, and x3 dot. We want to have a 3x3 matrix that defines the relation between those x dots with our state variables, x1, x2, and x3. So when we look at this x1 dot, we see that it's equal to x2. So we don't have any x1, 0. We have one x2, we don't have any x3. Same way, we can develop the row of the second row for the A matrix for x2 dot. Now x3 dot, we have minus 24 times x1 minus 26 times x2 and minus 9 times x3. But that's not it. We want BU2 plus we have another vector times our input. Now, x dot 1 doesn't have any input affecting that. Also, x2 dot input do not affect that, so it's 0. but on x3 dot, we have the input. So RT here, and the coefficient is 1. So now we have our state space model for the first block. Okay? Now, as I mentioned, I don't want it to stop here, but also I want to have the formula for the output for y equal to the cx times that formula, that famous formula, y equal to cx plus du. Okay? Now, I am going to use the second kind of like block diagram, knowing that my output is CS. Are we good? Or like this is in a time CT, okay? So let's try to build what's happening on that block diagram. So this is that block diagram transfer function says that the CS over BS is gonna be S squared plus 7S plus 2. That means CS is equal to the BS times S squared plus 7S plus 2. Okay, so if we run a Laplace inverse from this one, then we know that the C of t is going to be equal to B double dot plus 7B dot plus 2B. Okay, now let's go back and see what type of state variable we defined for our state space. We know B double dot is x3, B dot is x2, and B is x1. So I can rewrite it and say the C of t is x3 plus 7 x2 plus 2x1. We good? Now, C of t, I define it as output. So this is y. And I want to develop such a function. So, such an equation. So, my y, the vector y, which is only one kind of like variable, is going to be a matrix times my state variable plus another matrix times my input, the whole input of the system, which is RT. Okay, now I don't have any RT, so this is 0, so I don't need this. Is that clear? In the equation of the y, I don't have any input. Are we good? Now, here I have 2x1, so it's going to be 2. I have 7x2 and 1x3. So now I have the full state space model for that initial block diagram that I had. Is that clear? Are we good? I want to erase that so I can move on to the next concept. So if you're okay, I am gonna move on. Is that okay? So let's talk about, so far we only talked about how we can develop the state space from a transfer function. Now we want to go the other way around. So we want to like have the transfer function from the state space. Conceptually, it's very easy, but from the mathematical derivation is much energy and time consuming than what we discussed about converting the transfer function to a state space model. Now, we want to transfer a state space transfer function. That means our input is whatever function that we have, whatever model that we have for our state space. And we know we can develop that. We have that actually. The equation that defines the state space model is going to be x dot equal to ax plus bu. And also we have our output y is going to be equal to cx plus du. Very good. That was our state space model in a matrix form. Now, when I say it's a very easy concept, is because the only initial act that we need to do is to simply take a Laplace transform from this function. Very good. Now, what is the Laplace transform of the first equation? This one, if we take the Laplace, is going to be s x of s, these are in time domain, equal to the a x of s plus b u of s. Say b, I write b. Okay. Same goes for the next equation. We take a Laplace transform, and this one is very simple. So our output in an S domain is equal to the C, our input, our state variable in S domain plus D, the input in S domain. Now, what we want is a transfer function. This is our goal that defines the output based on the input. That was the definition of the transfer function. Are we good? Now, let's look at this. Our output, okay, beside the input that basically we want in a transfer function equation, has another a variable, which is our state variables vector. So we need to get rid of this one and write it based on the input so we can define the output versus input. Is that clear? How we can do that? Using the first equation. From the first equation, if we solve for x of s, we can see that if we bring the other the ax to the other side, is going to be s x of s, but s is a scalar. These are matrix, so we need to change that to the matrix. How we do that? We multiply by identity matrix. So it's going to be si minus a times x. This is going to be bu in S domain. So if we solve for x, that means our x in S domain is going to be, we have to multiply both sides by the inverse of this coefficient. So the other side, the inverse time matrix itself is going to be 1, or identity matrix in matrix language. So here we are going to have the x of s, but this side we are going to have si minus a inverse time b times the input in the S domain. Now we can put the x of s into this equation. Okay, so our y become c times si minus a inverse times b, okay, times u in a S domain plus d u in a S domain. So we can factorize the u. So it's going to be c Si minus A inverse B plus D, all of it times input. So our transfer function was output divided by input. That means our transfer function is going to be C times Si minus A inverse times B plus D. Now, the concept is very easy. But when you actually want to derive that, then you have like a third order matrix or fourth order, like 4x4 matrix at A or 3x3 matrix at A is not going to be easy. Okay, you have to like practice and like, because it's going to take a lot of time. Now, we are going to solve an example for the 3x3 matrix so we know what we are going to do. Are we good for the concept wise? Any question for that? No question? Are you okay for me to erase the board? Good. Yeah. Now we are going to solve a very beautiful example. So we know what that means actually. Now, let's say our state space model is x dot equal to my A is 0, 1, 0, 0, 0, 1, minus 1, minus 2, minus 3. Let's just use x plus 0, 0, 10 here. And my output is going to be 1, 0, 0, x. Now, I said the transfer function is going to be C times Si minus A inverse times B plus D. Now, my D is 0, so I don't have to like worry about it. Okay, but I need to like solve step by step for Si minus 1 inverse B. Now, I'm going to start with the Si minus 1. So, Si minus 1 is basically going to be S times the identity matrix. So it's S 0, 0, 0, 0, 0, 0. Minus my A is 0, 1, 0, 0, 0, 1, minus 1, minus 2, minus 3, which is very easy to do that. S minus 0 is S, 0 minus 1 is minus 1, 0 minus 0 is 0, this is 0, this is S, this is minus 1, this is going to be 1, this is going to be 2, and this is going to be S plus 3. Are we good so far? Now we get to the fun part when we wanted to like actually get an inverse of that matrix. Now we know that the inverse of a matrix Si minus A is going to be adjoint of that matrix Si minus A over the determinant of that Si minus A. Now, not all matrices have the inverse. Anyone remember what was the condition that you can check to see if the matrix actually has inverse or not? Determinant should not be zero. That being said, okay, it means that the smart thing to do is to first calculate the determinant. Okay, now the determinant of Si minus A is going to be the first row. We are going to use the first row and take out the columns one by one. So it's going to be the first component times the determinant of, we are going to eliminate these two, the column 1 and the row 1. So we are only have a 2 by 2 matrix. So it's going to be, what is that? 2 by 2 S minus 1, 2 S plus 3. And for the next one, we are going to have the same. This is minus 1. So minus 1 times, now we are going to eliminate this row and the second column. So it's going to be 0 minus 1, 1 S plus 3. And the next one is going to be 0 times, now we are going to eliminate this one. So it's going to be 0 S1, 2, but it's multiplied by 0. So even if you don't do that, which one? This one is plus 1, but the multiplication is minus 1. So I just apply that. So it's going to be plus minus 1 times that. Okay, so that minus, you get what I'm saying? This is like this. Plus minus 1 times whatever determinant that we have. So that minus can get change the plus. Is that clear what I did? So what happened to my okay. Now you know how to run as a determinant of 2 by 2 matrix. So this one is going to be, determinant is going to be the first diagonal multiply each other minus the second diagonal multiply each other. Are we good? Is that clear? Remember that? No. So that one is going to be S times S squared plus 3S minus 2, which is plus 2. The other one is going to be 0, okay, 0 minus 1, which is plus 1. And the coefficient is minus 1, so it's going to be minus 1. Are we good so far? And the third one is 0 times whatever determinant, so you don't need to like actually worry about that. That is 0. So this is going to be our determinant. Now you can simplify that. Is going to be S cubed plus 3S squared plus 2S plus 4. So that's going to be the determinant of our matrix. Yeah, go ahead.
Isn't it really minus?
Yeah.
For the sake of term?
This one?
Yeah.
It's minus 1
Mm,
plus 1.
sure.
Yeah, the first column matrix is plus, then it's minus, then
Oh. So this is going to be plus, this is going to be, right? Minus, minus. So this is going to be minus, this is going to be minus. Thank you. So now we have the determinant. We need to do the denominator of our inverse function. Can I erase this one? That's more fun. In order to calculate this one, we are going to have a 3x3 matrix. Hopefully I have enough space. And each component is going to be based on that Si minus 1. What we are going to do is we are going to first think I'm making mistakes or my notes. Okay. To do the adjoint, if I'm making mistake, let me know. Okay, we have to eliminate the first column and the first row for the column 1 component. Is that okay? And do the determinant of the rest. So it's going to be determinant of it's actually true. S minus 1 to S plus 3. Okay. Now the second component is going to be this is component 1 and 1, right? So you eliminate the first row and first column, it's 1 and 1. And this is going to be the determinant of the remaining. Now, the next one is A1, 2. So first row, second column. So it is going to be 0 minus 1, 1 S plus 3. And the last one, if you do that, the same kind of like concept is going to be 0s 1 2. Now I am gonna just write down the rest. You know how to do that. 1 2 s minus 1 0s s 0 1 s plus 3 s 0 0 minus 1 minus 1 0 s plus 3 minus 1 0 s minus 1. Are we good? No. It's just the determinant of whatever you have. Okay. Now you can calculate each determinant you have. So eventually your matrix is gonna be this is easy. S times S plus 3 minus 1 times 2. If you do that, it's gonna be S squared plus 3S plus 2. The other one is gonna be 1 minus S minus 3 s squared plus 3s, 2s plus 1, 1 minus s squared. Okay, now we said Si minus A inverse is that matrix divided by determinant. So basically, it means each component is divided by that. Let's call this delta because I don't want to write down every time. So, are we good so far? Are we good? So, my Si minus A inverse is going to be 1 over delta times this matrix S2. Let me put the delta in. S2 plus 3S plus 2 over delta 1 over delta minus S over delta minus S minus 3 over delta x squared plus 3S over delta 2S plus 1 over delta 1 over delta minus S over delta and S squared over. The fun is that we are not done yet. We said our output, actually the transfer function that we had is going to be C times Si minus A inverse times B plus B. Okay, so now we need to calculate C times that inverse matrix. Okay, and then multiply it by B. So, can I erase the bottom half of the board? It is boring, but you need to practice so you get fast on getting inverse of a matrix, because believe me, you are gonna need to save a lot of time doing that. Okay. My C times Si minus A inverse is gonna be, if you remember, my C was 1, 0, 0, and I have my Si minus 1. Minus S minus 3 over delta S squared plus 3S over delta 2S plus 1 over delta 1 over delta. Let's do it. This is 1 by 3 matrix, and this is 3 by 3 matrix, so the result is going to be 1 by 3. So this is going to be 1 times this one plus 0 times this plus 0 times this, so it's just going to be the first one. So it's going to be S squared plus 3S plus 2 over delta. You can imagine the second component is going to be the same because these two are going to be multiplied by 0. So it's going to be minus S minus 3 over delta. And the other one is 1 over delta. So far, we are here. We have to multiply this one by B. So the overall first term, let's consider this one is 0, so the TS is gonna be that matrix of minus S minus 3 over delta, 1 over delta times RB, which was 0, 0, 10, if you remember. Are we good? Now, it's 1 by 3, 3 by 1, so we are gonna have only one component. So it's 1 by 1, okay? Whatever the result is. So this one is multiplied by 0, so doesn't matter. This one is also multiplied by 0, doesn't matter. So we only have 10 over delta. If we have our delta, so it's gonna be 10 over S cubed plus 3S squared plus 2S minus 1. So now we have our transformation. Are we good? Any question about that? No? If you don't have any question, I don't want to start the examples because the examples are we are gonna start from the first topic, like converting the time, converting the transfer function to the state to state. Okay, the first conversion that we talked about, and before that, developing the state space and the transfer function from a system from a certain system. So if you don't have any question, I wanted to stop that because I don't want to like mix the concept with each other. Any question?
Is that the only way to find the inverse of that matrix?
Yes. That this part that we talked about, that SI minus A inverse, you mean, or the whole kind of like concept?
No, the SI minus A.
Yes, that's the only way that you can find it. I think there are some techniques for higher matrix dimension, like 4 by 4 and 5 by 5. You are not going to get 4 by 4 and 5 by 5 in the exams or homeworks. Okay, so it's too much. Okay, although it's good for your bicep, but it's too much. So highest order that you can get is 2 by 2.
You want us to write this out in hand, and you don't want me to use the inverse matrix function on MATLAB.
Not yet. That's what I'm saying. Yeah, try to. Yeah, this is good for bicep, as I said. Yeah, it's a workout. Try to write it. Yeah. So, and the reason is I want you to practice mathematical kind of like analysis. But you are gonna need it because this is introduction to control system properly. Probably you are gonna get the control theory with Dr. Tang. On that part, there is no MATLAB. Dr. Tang doesn't use MATLAB. Okay, so everything is gonna be analysis on the paper. So try to practice that actually. Okay, so you are gonna need it. Any other question? No. So far, we are gonna before midterm we only have like a on paper analysis. So we are gonna use just regular analysis. But after midterms, we are gonna start working with MATLAB because now we have the foundation. Okay, and then we are gonna use it for the actual system analysis. Okay, and I am gonna give you a project which is a PID controller, and you need to analyze. Okay, right. find the transfer function, find the state space model, okay, and then run a stability. We are gonna learn how to run a stability, like Nyquist and like Roots on all those both plot, and then you are gonna use MATLAB to kind of like analyze. Make sense? Okay. Any question? No? Okay. If not, that's it for today.